So in today's video we are going to deal with one of the new chapter called as your metallurgy. Yes. So of course in our classes, in the previous classes we have seen that. So metallurgy means what? In this topic we are mainly saying that we are going to extract the minerals from the earth. These minerals will be having certain ores in them, and these ores we are able to, by some suitable methods, we are going to extract the metal by a process called as your metallurgy. So while doing the process, of course we have seen that the first and the foremost thing, as soon as we are obtaining the ore, the first method we did was the concentration of ore. And in this concentration of the ore, we have seen that we have undertaken froth flotation. Yes, there were many methods. Froth flotation method was there. Magnetic separation was there. Your leaching process was there. And many other methods were carried out. But in all these methods, what we were doing is, so of course we know that from the earth, we have taken out the minerals, and from these minerals what we are doing is we are extracting the ores. This ores, of course, this will be having the metals, but along with these metals there will be like your sand particles, your stones, and all those things. So in the concentration of the ores, what we are doing is we are removing such sand and the stone particles to some large extent. Of course, we cannot say that 100% we are removing all the sand and the stones, but nearly 150 to 55% to the concentration of the ore. By involving such methods, we are able to remove the sand and the stone particles, so that whatever the ores we are be doing or subjecting to the further process will be having lesser concentration of the impurities. So once we have done the concentration of the ores, then second part which involved was your roasting and calcination. Roasting and calcination. That means what? Whatever the concentrated ores we have obtained, we were converting their ores to their respective oxides. So in roasting, what we were doing is we were burning the ores in the presence of oxygen. We were burning the ores in the presence of oxygen. And in the calcination, what we were doing, whatever the ores we have obtained after concentrating, we were burning them in the absence of oxygen. So these were the two important things which we have learned in our classes. But in today's video, the most important thing we have to going to choose is that the reduction of your metal oxide to metal. Reduction of the metal oxide to metal. That means what? In both your roasting and calcination, of course what we were doing, here we were getting as their respective oxide. For example, in a roasting, if I was having a zinc ore of zinc sulfide, by treating it with oxygen, I was getting as a zinc oxide. In this calcination, if I was having a zinc carbonate, in the absence of oxygen, I was getting a zinc oxide plus CO2. But in both the process, what we have obtained, of course, whatever the ore I have taken, it is an ore of a metal called as zinc. So first what did I do? I am treating them with the oxygen in the roasting and converting to their respective oxides. You can see in both the case. Now in my third process, what does it involves is I have to remove this oxygen from the metal in order to obtain my metals in a higher percentage. So that is given by the heading called as reduction of the metal oxide to the metal. Very much important. So how we are going to reduce this metal? Of course, guys. So this reduction of the metal oxide is only done by using some other substance called as it of your reducing agent. For example, I am having a metal oxide of MXOY if I choose. Okay, where M is your metal, O is your oxygen. Of course, X and Y is the respective stoichiometry. in case if I choose that my carbon or the coke, if I say carbon, solid carbon, coke is my reducing agent, what it will happen, I will be giving my reaction as XM plus YCO. So you can just notify over here that this was my metal oxide. So in order to reduce this, I have used one more substance, or I can say as a reducing agent. So when I am choosing it, of course at some particular temperature the reaction takes place to give me my respective metal, and in turn what happens, whatever the reducing agent you have undergoes oxidation. So overall this process consists of two steps. First step is what? First is your reduction of metal oxide. Alva, reduction of metal oxide. We know by the form your definition of reduction. So when you are going with the respect to the elements, addition of oxygen is called as oxidation, or removal of oxygen can be also called as your reduction. Alva. So here what is happening, I am removing an oxygen. So what it is called as reduction of metal oxide is the first process. Can you say what will be the second process within this reaction? Of course. So whatever the reducing agent you have took, that is undergoing oxidation. So second process involves the oxidation of your reducing agent. Alva. Oxidation of your reducing agent. So these will be the two processes which will be taken whenever I am choosing a metal oxide to get reduced to the particular metal. Now the question is, as I have said in my earlier classes, this metallurgy is an industrial process. True. So every time an industry thinks that there should be a minimum investment and a maximum profit. So that means what? Of course, for the reduction process, I have chosen a reducing agent, no problem. But my reaction should go spontaneously. Alva, I can just supply you the temperature. Of course, I can give you the temperature, none other than the temperature and the reducing agent. I don't want to invest my money in anything else. So what should happen? So as soon as I am giving you the reducing agent and a particular temperature, the reaction should be spontaneous. So how can a reaction be spontaneous? We know from the thermodynamics that by Gibbs-Helmholtz equation, delta G is equals to delta H minus T into delta S. Is that true? Gibbs-Helmholtz equation. Of course, there will be a question, sir, why did you choose a particular reducing agent, in this case as a coke? The same question will be answered over here. That is, whenever we are choosing a particular oxide, it is not that all the time we are using the coke itself. Different ores will be utilized or will be extracted. That is, different ores, we can extract the metals by using your different reducing agent. And the reducing agent, which reducing agent you are going to choose, depend upon this equation. We know that whenever a reaction is said to be spontaneous, what should be the sign of your delta G? That is, delta G should be negative. Alva. So whenever your delta G is negative, the reaction is spontaneous. That means what? So for example, if I am going to split this reaction, that is my first reaction, if I take it as MXOY, okay. First what I am going to do is, my first reaction involves the reduction of this metal oxide. That is, I should get as XM plus YO. So for this reaction, if I am going to calculate some delta G, let me consider, okay, let me say it as G1. Okay, Gibbs free energy for this reaction. The next involves what? So the reaction, whatever you have taken over here, that is your C plus YO should give you YCO. If I choose, of course, here also Y. So this will be your G2. That means what? Why I have chosen the C in this particular reaction is that the sum of the energies, whatever you are taking over here, let us take it as delta G1 itself, because it will be a confusion, because we know that delta G is the difference itself. So if I'm going to say is the sum, you'll get confused over here. So let us take this one as delta G1 itself, this one as delta G2 itself. So now what I can say is, how does your reaction is spontaneous? It is only spontaneous when I take delta G of the overall reaction. That is delta G1 plus delta G2 is giving you negative. So whenever I am choosing a reducing agent and whenever these two reactions are taking independently and measuring out their Gibbs free energies, and the sum should give you the negative, that means what? The reaction will be spontaneous. So whatever the reducing agent we have chosen will be correct for that metal oxide. Is that clear? So by this way, one can easily see which reducing agent has to be chosen for a particular metal oxide. Now the question arises that when does this delta G becomes negative? Of course, we can just see over here. So whenever your delta S is highly positive, at that time what happens? This term will be very much higher, T into delta S. Since it is associated with a negative sign, delta G will be negative. So this is the way of understanding that what reducing agent we have to use for a particular metal oxide. Let me say it once again. So in this process, after the concentration of the ore and after converting your respective metals to their respective metal oxides, what we have done is we are converting that metal oxide to the metal now. So this metal oxide to the metal is done by utilizing some another specific substance called as your reducing agent. So in order to choose this reducing agent, we have to understand that in this reaction it undergoes two processes. One is reduction of your metal oxide to the metal, and the another part is the oxidation of your reducing agent. So whatever the reducing agent I have chosen, it should be in such that the reaction should be carried out spontaneously. That is, as soon as I put the reducing agent and give you the temperature, the reaction should take place on its own. That is, I should get the metal and my whatever the reducing agent is that should extract this oxygen. So in order to say that your reaction is spontaneous, how can we say? That is through your Gibbs equation. That is delta G is equals to delta H minus T into delta S. When does your delta G is negative, then only we can say that the reaction is taking place spontaneously. But when does it becomes negative? Only when your delta S is positive. Delta S is positive means what? Maximum randomness. That is, entropy should be more. Or in simple words, what you can say, whatever process is taking place should exist in the maximum randomly the molecule should move. Then only what happens? Your delta G will be negative. But how to calculate this delta G part? Of course, whatever the two reactions we have taken within a major reaction, we are going to independently calculate their Gibbs free energy. So once we are calculating the Gibbs free energy, what does this indicate? So when you are taking the sum, overall Gibbs free energy for the reaction should get negative. So now here we came to know that, so when this delta G1 and delta G2 sum you are taking, that is when you are choosing your reduction of your metal oxide to the metal and calculating its delta G and the oxidation of your reducing agent, you're calculating it as delta G2, the coupling of these two reactions. Coupling means nothing. When you're adding these two reactions, if you're getting the negative, that means what? Whatever the reducing agent you have chosen is proper for that particular or at that particular temperature. So by this way, one can easily predict which reducing agent he has to choose in order to reduce the particular metal oxide. So but once again there will be a dilemma. So whether we have to choose for all elements? Of course not. Because there was a scientist. He has given us a diagram called as that of your Ellingham diagram, which gives you the choice of a suitable metal or the element to reduce another element or the another metal, and that is through your diagram called as Ellingham diagram, which you will be seeing in our next video.